Look at the family portrait of our solar system. Line the planets up the way the old textbook diagrams do, all of them turning in the sunlight, and watch how they spin. Mercury, upright. Venus, nearly upright, turning the wrong way but still standing. Earth, tipped a gentle 23 degrees, just enough to give us summer and winter. Mars, tilted almost exactly like us. Jupiter, barely leaning at all. Saturn, tipped like Earth. Neptune, a modest lean. Every one of them atop, spinning more or less the way a top is supposed to spin. Axis pointing up and down. Poles at the top and bottom where poles belong. And then there is the seventh planet. Uranus does not spin like a top. Uranus lies on its side. Its axis is tipped a staggering 98 degrees, past the horizontal, actually tilted a little beyond flat, so that instead of turning upright as it travels round the sun, it rolls. It rolls along its orbital path like a bowling ball down a lane. Its poles do not point up and down, they point out sideways, sometimes straight at the sun, and sometimes straight into the dark. For a world nearly 4 times the width of Earth, this is not a small quirk. It is the single most disquieting fact in the entire family portrait. A planet knocked flat and left that way, still rolling, billions of years later, exactly where the blow left it. Say that number slowly. 98 degrees. A right angle is 90. Uranus is tipped past the right angle. It is not leaning. It has fallen over, and here is the through line of everything you're about to hear. The thread that runs beneath every strange thing this world will show us. Uranus is not an oddity that happens to be tilted. Uranus is a wound that never healed. Somewhere in its deep youth, 3 or 4 billion years ago, something went catastrophically wrong here. A collision so enormous it may have involved a body twice the size of Earth, and the planet was, in the most literal sense, knocked down and never got back up. What makes Uranus extraordinary is not just that this happened. It is that the damage is still shaping everything. The wound is still open. The frozen heart that gives off almost no warmth. The seasons that last for decades of unbroken light and decades of unbroken dark. The magnetic field pointing in the wrong direction. The diamonds that may be falling like rain deep inside. Trace each of them back far enough, and you arrive at the same single moment. One catastrophe, still writing the physics of an entire world. Over the next few hours, we're going to follow that wound. We're going to go back to the garden in England where this planet was first noticed. Back to the 9 hours a single spacecraft spent racing past it, out to the impossibly cold interior that generates no heat of its own, down into a mantle where carbon may be crushed into gemstones, and finally to the question that planetary scientists are still arguing about in conference halls today, whether the thing that struck Uranus is still down there, buried, part of the planet now. If these long, slow journeys through the strange corners of the universe help you unwind at the end of the day, a like and a subscribe genuinely help these quiet explorations reach other people who need them, and then settle in, get comfortable, let the room go dark. Now let us begin. To understand how astonishing that tilt is, you have to understand what a planet's tilt normally means, and how gently it normally happens. When a solar system forms, it forms out of a spinning disk of gas and dust, a great flat pancake turning slowly around a young star. The material in that disk is all going the same way, all orbiting in roughly the same plane, and the planets that condense out of it inherit that motion. They spin more or less in the direction the disk was spinning. Their axes come out roughly perpendicular to the disk, roughly upright, because that is the path of least resistance, the natural outcome of matter settling into rotation. A small tilt is normal. A nudge here, a glancing encounter there, and you get Earth's 23 degrees, enough to swing the seasons but nothing that upends the whole arrangement. 98 degrees is not a nudge. 98 degrees is a planet that has been rotated onto its side relative to the way it was born. The disk laid down the rules, and Uranus violates them completely. For a world of this mass to end up this way, something had to reach in and shove it. And the shove had to be colossal, because a planet this large carries an enormous amount of angular momentum, an enormous stubbornness and unwillingness to change how it turns. To tip it over, you would need to hit it with something of planetary scale. You would need, in other words, a catastrophe. The leading explanation is exactly that. A giant impact, roughly 3 to 4 billion years ago, when the solar system was young and still crowded with leftover building material. Great half-formed worlds that never became planets, wandering through the outer dark. One of them, according to this hypothesis, may have been as much as twice the size of the Earth. It came in and struck the young Uranus and knocked it flat, transferring so much of its own momentum in that single blow that it toppled the entire planet from upright to sideways in what, on cosmic timescales, was an instant. But the collision may have done far more than tip the planet over. Some models suggest the impact reached deep, that it dredged up the planet's interior, churning it, disturbing the layered heat locked inside from the moment of formation. And this may be the reason for one of the deepest mysteries of all, the reason Uranus is so uniquely, impossibly cold. Every other giant planet in the solar system radiates more heat than it receives from the sun. They glow, faintly, with leftover warmth from their birth and their slow contraction. Uranus does not. Uranus gives off almost nothing. It is the coldest heart of any giant, and one of the leading suspects for why is the same event that knocked it sideways. The blow that toppled the planet may have let its ancient inner warmth escape into space, leaving behind a world that has been quietly freezing ever since. Let that settle for a moment. A single collision that may have tipped a planet on its side and drained the heat from its core, and the effects of both are still measurable today, billions of years later, from across the solar system. Now, honesty requires a caution here, and it is a caution we will return to again and again, because it is the honest posture toward this entire world. Not everyone agrees on the single giant impact. Some scientists propose alternatives, gravitational interactions with other bodies that slowly tug the axis over across long stretches of time, or a large moon that migrated inward over eons and eventually crashed into the planet, delivering its shove not all at once but as the final act of a long, slow drift. The debate is real, and it is unresolved. Some point out that a single simple collision struggles to explain everything at once: the missing internal heat, the precise arrangement of the moons, the details that stubbornly refuse to line up. Whether it was one cataclysm or a complex chain of events, though, the conclusion at the centre holds. This is a world that was permanently scarred in its youth. Its frozen interior and its diamond-rich mantle still reflect the violence of its origins. As the planetary scientist Patrick Irwin has put it, plainly, Uranus is still an outlier, a vital case study for just how chaotic and violent the early history of our solar system really was. An outlier, hold on to that word. Everything about Uranus is a departure from the rule, and every departure seems to point back to the same source. But before we can dig into the wound, we have to answer a more basic question, one that sounds almost too simple. How did anyone even find this planet in the first place? Because for nearly all of human history, nobody knew it was there at all. Travel back with me then, to the evening of March the 13th, 1781, to a modest house in the city of Bath, in the west of England. It is cold, the sky is clear, and in the garden behind the house stands a man who was not, by profession, an astronomer at all. His name was William Herschel. He had been born in Germany, in Hanover, and he had come to England as a young man to make his living in music. He was an organist and a composer, a teacher of music, a working professional who spent his days giving lessons and his evenings performing. Astronomy was, at first, a passion pursued in the hours he could steal from his real work, but it was a passion that had grown into something close to an obsession. Herschel was not content to look through telescopes other people had made. He built his own, grinding and polishing the mirrors himself, sometimes for hours on end, so absorbed in the work that his sister Caroline would feed him by hand so he would not have to stop. He built better instruments than almost anyone else alive, and with them he was undertaking something patient and enormous, a systematic survey of the entire sky, sweeping across the heavens star by star, cataloguing what he saw, hunting for double stars and anything else the sky might be hiding. On that night in March, sweeping through the constellation Gemini, he came upon something that did not look quite right. It was a faint object, and it was not a point of light like the stars around it. Through his excellent homemade telescope it showed a tiny disk, a smudge, something with a little bit of size to it. Herschel did not leap to any grand conclusion. He was a careful man, and careful men do not announce discoveries they cannot defend. In his observing records he wrote it down plainly, cautiously, hedging his bets. In the quartile near Zeta Tauri, he noted, the lowest of the two is a curious either nebulous star or perhaps a comet. A comet. That was his best guess. Something fuzzy, something that moved, and this object did move. Over the following nights he watched it shift slowly against the fixed background of the stars, and its motion confirmed that it was not a star at all but some nearer, wandering thing. A comet was the natural assumption, because comets were known to wander and known to show a fuzzy disk, and because the alternative was almost unthinkable. The alternative was that Herschel, an amateur, a musician with a homemade telescope in a garden in Bath, had found a new planet, and no one, in all of recorded history, had ever done such a thing. Think about what that means. The planets known to humanity, Mercury, Venus, Mars, Jupiter, Saturn, had been known since antiquity. They were bright enough to see with the naked eye, and every civilization that ever looked up had watched them wander through the sky and given them names. The idea that the solar system might have an edge, that it might extend beyond Saturn, that there might be worlds out there too faint to see without a telescope. This was simply not part of how people imagined the heavens. The map was assumed to be complete. The wandering lights were counted and named. There was nothing more to find, and then a musician found something more. As the observations accumulated and other astronomers turned their instruments toward the new object, the truth slowly became undeniable. This was no comet. Comets follow long, stretched, eccentric paths, and they grow tails as they near the sun. This object moved on a nearly circular orbit, calm and stately, far out beyond Saturn. It was a planet. It orbited the sun at roughly twice the distance of Saturn, the previous edge of the known world, which meant that in a single stroke, Herschel had doubled the size of the solar system. Overnight, the map of everything expanded outward to twice its former reach. The territory of the sun's family, unchanged in the human imagination for thousands of years, was suddenly twice as large as anyone had ever believed. Stop and feel the weight of that. Every human being who had ever lived up to that night had lived inside a solar system they thought ended at Saturn. And in one evening, in one garden, that boundary was pushed out into a darkness no one had known was there. This was a watershed. Uranus became the first planet in history discovered with the telescope, the first world that human eyes could not have found unaided, the first proof that the sky held more than the ancients had counted. The discovery made Herschel famous almost immediately, transforming him from a provincial music teacher into one of the most celebrated men of science in Europe. And Herschel, grateful and shrewd in equal measure, tried to name his planet after his king. He proposed to call it Georgium Sidus, the Georgian star or the Georgian planet, in honour of his patron, King George III of Britain. It was a gesture of loyalty and no doubt of practical ambition. Royal favour could secure a lifetime of funding for a man who wanted nothing more than to keep building telescopes and sweeping the sky. And in Britain the name persisted for decades. British almanacs and British star charts dutifully called the New World the Georgian planet long after the rest of the continent had moved on. But the rest of the astronomical community had a different instinct. There was a tradition to honour, the tradition of naming the planets after the gods of ancient myth. Mercury, Venus, Mars, Jupiter, Saturn, a lineage of deities stretching back through Rome and Greece. To insert a modern British king into that ancient roll call struck many astronomers as jarring, parochial, wrong. The German astronomer Johann Elert Bode proposed an alternative that fit the pattern the sky had always followed. He suggested Uranus, after the Greek god of the sky, and fittingly the mythological father of Saturn, just as the planet Uranus orbits out beyond Saturn. The genealogy of the gods mirrored the genealogy of the worlds. The name had a rightness to it, a logic that Georgium Sidus never had. And slowly, over the following decades, Uranus won out. It became the globally accepted standard, and it is the name we use today. So the seventh planet had a name, a place on the map, and a discoverer who had become famous overnight. And then, for a very long time, almost nothing happened. Because here is the quiet, humbling truth of the 2 centuries that followed. Uranus had been found, but it could not be read. It was simply too far away, and through the telescopes of the 18th and 19th and even much of the 20th century, it remained a featureless, distant dot. A pale, tiny disk showing no detail, offering no clues. Astronomers could track its motion, refine its orbit, calculate its size and its distance and its mass. They could eventually detect that it had moons circling it. But the planet itself, its surface, its clouds, its weather, its true nature, stayed hidden. A dot, a rumour of a world, a profound mystery that defied close observation for as long as observation was confined to the surface of the Earth. For 200 years then, Uranus was a name on a chart and almost nothing more. Its greatest secrets, the sideways spin, the frozen heart, the wound in its youth, remained utterly beyond reach. To read this world, humanity would have to leave the Earth entirely and go there, and that would not happen until the space age was nearly a decade old and one small spacecraft, having already sailed past 2 other giants, kept going into the outer dark. That spacecraft was Voyager 2, and its encounter with Uranus is, even now, one of the most remarkable and poignant chapters in the history of exploration, because in a very real sense, nearly everything we know about this planet we learned in a single afternoon. The date was January the 24th, 1986. Voyager 2 had been travelling for more than 8 years, launched in the summer of 1977, threading its way past Jupiter and then past Saturn, using the gravity of each giant to fling it onward toward the next. Now it arrived at Uranus, the first and, to this day, the only spacecraft ever to make the journey. At its closest approach it passed within about 50,600 miles of the cloud tops, some 81,500 kilometres, skimming past the pale planet at tremendous speed. And then it was gone. The whole close encounter, the window in which Voyager could gather its most detailed data, lasted only hours, a fleeting pass, a single afternoon at a world it had taken nearly a decade to reach. There was no going into orbit, no lingering, no returning for a second look. Uranus was a stop on a longer road, and the spacecraft could not stay. It raced past, snapping its images and taking its measurements as fast as its instruments could work, and then it fell away into the darkness on the far side, bound for Neptune. Those few hours delivered nearly all the hard data we still rely on today. Everything else, the models, the debates, the hypotheses about impacts and diamonds and buried impactors, is built to a remarkable degree on the interpretation of that one brief visit. We are, in a sense, still living off the data Voyager 2 gathered in a single afternoon in 1986. And what did it see when it finally got close enough to truly look? An eerie thing. a world almost without features, where Jupiter had shown its churning bands and its great red spot, where Saturn had shown its storms and its glorious rings. Uranus showed almost nothing, a pale cyan sphere, a smooth, soft blue-green orb, nearly blank, with no visible storms, no swirling weather, no dramatic detail at all. It looked less like a living, turbulent giant, and more like a perfect, still, painted ball. Scientists who had waited years for this moment found themselves looking at what appeared to be the blandest planet in the solar system. That distinctive colour, that pale cyan, has a specific and elegant cause. High in the Uranian atmosphere there is methane gas, and methane has a particular appetite. It absorbs the red wavelengths of sunlight, drinking in the warmer end of the spectrum, and it scatters back the blues and greens. So the light that reaches your eye, or reaches a spacecraft's camera, is the light methane did not swallow. The planet glows that soft, cold cyan because it has quietly removed the red from the sunlight falling on it. Its very colour is a kind of subtraction, a hue defined by what is missing. Now, the blandness was, we would later learn, partly an illusion of timing, and we will come to that. But even in that first fleeting pass, Voyager 2 did far more than photograph a pale sphere. It discovered 10 new moons, previously unknown, small dark worlds circling the tilted giant. It found 2 new rings to add to the faint ring system already suspected around the planet, and it mapped something genuinely bizarre, a magnetic field wildly, strangely tilted, unlike anything expected, a field that seemed almost as knocked askew as the planet itself. Each of these discoveries would become a thread in the larger story. Each would eventually be pulled back toward that same central wound. But there is a shadow over this triumph, a piece of history that makes the Voyager encounter almost unbearably poignant. On Earth, at the very moment this spacecraft was achieving something no human machine had ever done, reaching a new giant world at the edge of the known solar system, almost no one was paying attention to Uranus. Because just 4 days after that closest approach, on January the 28th, 1986, the Space Shuttle Challenger broke apart shortly after launch, and 7 astronauts were lost. The nation's grief, and the world's, turned entirely toward that tragedy. The quiet, extraordinary success of a small spacecraft at a distant planet was almost completely overshadowed. Voyager 2 had touched the edge of the solar system, and history, understandably, was looking the other way. For decades afterward, scientists treated the Voyager data as a portrait of a typical Uranian day. This was what Uranus was like, they assumed. This pale, calm, featureless world was simply how the planet normally behaved. But there is a final twist, and it is one that reframes everything. Recent reanalyses of the Voyager measurements suggest that the spacecraft may have arrived at an extraordinarily unlucky, or perhaps extraordinarily interesting moment. There are signs that Voyager 2 flew past during a rare and extreme burst of solar weather, a moment when the stream of particles pouring off the sun happened to be unusually intense, compressing the planet's magnetic bubble, its magnetosphere, and supercharging its radiation belts. If that is true, then the one detailed snapshot we possess of Uranus may not show a typical day at all. It may show a planet caught in an unusual state during a rare event in the single afternoon we happen to be watching. As the space scientist William Dunn has put it, we now know even less than we thought we did about what a typical day in the Uranian system might actually look like. Read that again and feel how strange it is. New analysis of old data did not add to our confidence, it subtracted from it. It revealed that our one clear look at this world may have been a look at an exception, not the rule. And so we are left in a peculiar and humbling position. Everything we're about to explore, the frozen heart, the decades-long seasons, the possible rain of diamonds, the buried scar of an ancient impact, rests on a foundation of a single fleeting visit, possibly to a planet caught on an unusual day, filtered through 2 centuries of watching a dot from very far away. This is not a world we understand. This is a world we've glimpsed once, sideways, in passing, which makes the mystery of the tilt all the more compelling. Because to explain that 98 degrees, to explain a planet lying on its side, we cannot go back and take new measurements at will. We have to work with what that one afternoon gave us and reason our way backward across 3 or 4 billion years to the moment everything went wrong. We have to reconstruct a catastrophe from its faint surviving traces. And the first trace, the first thing we must measure precisely before we can understand anything else, is the tilt itself, how it was pinned down, what it truly means, and why it points so insistently toward a single, ancient, violent event in the deep youth of this wounded world. So let us begin with the tilt itself, and let us be careful about what that number actually describes. 98 degrees. Say it slowly. It sounds like a measurement, precise and cold, the kind of figure you might read off an instrument and forget a moment later. But hidden inside those 2 syllables is one of the strangest facts in the entire solar system, and to feel it, you first have to feel what a normal tilt is. Think about Earth for a moment. Our own planet leans by 23.5 degrees. That gentle lean is the reason we have seasons at all, the reason the northern half of the world tips toward the sun in June and away from it in December, the reason there is such a thing as summer and winter. 23 degrees, a little off vertical, like a person standing straight but resting their weight on one hip. It is enough to reshape our entire calendar, to grow our harvests and freeze our winters, and yet it is a subtle thing. A slight nod of the head. Now hold that image, and now tip it over, not a little. Not to 40 degrees, or 60, or even 80. Tip it past horizontal. Tip it until the axis that should point up and down is instead pointing almost directly out at the sun. That is Uranus. Its poles sit where every other planet keeps its equator. Its equator runs vertically from top to bottom, where every other planet keeps its poles. It does not lean toward the sun the way Earth does. It faces the sun. One pole at a time, it stares straight into the light for years on end, while the opposite pole hangs in a darkness that lasts just as long. The word we reach for, again and again, is that Uranus rolls. It does not spin like a top the way the other planets do, upright and dignified. It tumbles along its orbit like a ball rolling across a floor, and it has been rolling that way most likely for something close to 4 billion years. Let that settle for a moment, because this is not a metaphor invented to make the planet sound dramatic. It is a literal geometric fact, and Voyager 2 confirmed it with a precision no ground-based telescope had ever managed. From 400 years of watching a pale dot from very far away, astronomers had already suspected the tilt was extreme. They could infer it from the way the moons moved, from the strange path the planets seemed to trace. But suspicion is not the same as certainty. It took a spacecraft threading its way through the system in the space of a single afternoon to pin the number down and hand it to us as something solid. 98 degrees, a planet lying on its side. And here is where the mystery deepens instead of resolving. Because if Uranus were alone in this strange posture, a single planet knocked askew, spinning oddly, keeping its own peculiar company, you might file it away as a quirk, a one-off, a dice roll that came up strange. But Uranus is not alone. It is the centre of a vast and orderly family, and that family shares its wound. Consider what Voyager found as it swept through the system. It did not find a tilted planet surrounded by a normal upright ring of moons and debris, as though the planet had somehow been knocked over while everything around it stayed put. It found the opposite. It found an entire system tipped over together. The rings of Uranus, 13 faint dark bands of material, far dimmer and stranger than the bright halo of Saturn, do not circle the planet's orbital plane. They circle its tilted equator. They lie in the same plane as that fallen axis, wrapped around the middle of the sideways world like a belt around a body lying down. And the moons, 27 of them and counting, the largest of which carry the names Titania and Oberon and Umbriel and Ariel, with the small and troubled Miranda closest of all, do exactly the same thing. Every one of the major moons orbits in that same tipped-over plane. Not the plane the planet should occupy. The plane the planet actually occupies now, after whatever happened to it. They march around the fallen equator in neat, patient circles, all of them sharing the same alignment, all of them tilted by the same impossible 98 degrees. Think about what that means. Think carefully, because this is the first real clue, and everything else hangs from it. If something had merely nudged Uranus off balance in recent times, some passing gravitational tug, some slow drift, you would expect a mismatch. You would expect the planet to be tilted while its moons and rings, obeying older laws set down long ago, continued to circle in the plane they had always occupied. You would see a disagreement written across the system, a planet pointing one way while its family pointed another. But there is no disagreement. There is agreement. Total, eerie, system-wide agreement. The planet is tilted, and everything that belongs to it is tilted along with it, all facing the same direction, all bearing the same scar. That shared alignment is what scientists sometimes call the smoking gun, and it tells us something crucial about time. Whatever knocked Uranus onto its side did not happen last week, or last million years, or even last 100 million years. It happened long ago, long enough ago that the entire system has had time to settle into a new equilibrium around the new orientation. The moons did not simply stay where they were while the planet fell. In some deep sense, the moons themselves are children of the fall. Their orbits were set by the wound. They circle the scar because the scar came first, and then they came after. Stop and feel the weight of that. The damage to Uranus is not a mark on an otherwise unblemished world. The damage is the organizing principle of the whole neighborhood. It is the frame on which everything else is hung. When you look at the Uranian system today, at its rings and its 24 moons all wheeling in their tipped and tidy plane, you are not looking at a system that survived a catastrophe. You're looking at a system that was built by one, which brings us at last to the catastrophe itself. Because a fact this strange demands an explanation, and for decades now the explanation that has commanded the most attention, the one that best fits the evidence, that best accounts for the smoking gun, is almost breathtaking in its violence. Early in the history of the solar system, roughly 4 billion years ago, when the planets were young and the space between them was still crowded with wandering debris, something enormous struck the young Uranus. Not a comet, not an asteroid, not one of the small bodies that pepper a planet's surface with craters and leave the world essentially intact. Something far larger, a protoplanet, a world in its own right, still forming, still growing, at least the size of the Earth. Some models push the figure higher, to a body twice as massive as our entire planet or more. Picture that. Picture a second world, as heavy as ours or heavier, sweeping in across the dark and colliding with the ice giant with a force that almost defies the imagination. And here is the delicate, almost paradoxical part, the thing the impact hypothesis has to thread so carefully. The collision had to be violent enough to tip an entire world onto its side, to overwhelm the immense stabilizing spin of a planet nearly 4 times the width of Earth, and knock its axis from near vertical to fully horizontal. That takes an almost unthinkable transfer of momentum, and yet the collision could not have been so violent that it simply destroyed Uranus outright, scattering it into a ring of rubble that never came back together. It had to be a blow that toppled the planet without shattering it. A wound severe enough to change everything, but not quite severe enough to end everything. That is a narrow window. It is part of what makes the impact hypothesis so demanding to model, and part of why scientists find it so compelling when the numbers work. Because when researchers run the simulations, when they build a young Uranus inside a computer and hurl an Earth-sized body at it and let the physics play out, they find that a strike of just the right size, at just the right angle, can do exactly this. It can spin the planet over onto its side, and crucially, it can do so while leaving behind a coherent world, battered and transformed, but recognisably a planet. Now, you might reasonably ask why scientists reach for something so extreme. Why invoke a world-shattering collision at all, when there might be gentler explanations? And this is a fair question, because there are gentler explanations on offer. Over the years, researchers have proposed slower, quieter mechanisms for the tilt. Perhaps the gravity of the other giant planets, tugging steadily over vast stretches of time, could have wobbled Uranus's axis into its strange position. Perhaps a large moon, now lost, once orbited the planet and slowly talked it over before drifting away or being destroyed. These ideas have their advocates, and they should not be dismissed. As we will find again and again in this story, the honest answer is that nobody knows for certain what happened. We are reconstructing a crime scene 4 billion years cold, but the impact hypothesis has a particular strength that the gentler theories struggle to match, and it comes back once more to the family. It comes back to those moons and rings, all sharing the tilt. A slow gravitational nudge, spread across hundreds of millions of years, would have a hard time explaining why the entire satellite system lies so neatly in the tilted plane. It would tend to leave that telltale mismatch, that disagreement between planet and moons. But a single sudden impact, a moment of catastrophe rather than an age of drift, can, in the models, produce exactly the shared alignment we observe. It can tip the world and, in the same event, lay the foundation for the moons to form in the new plane. The violence is the very thing that explains the order. There is a further piece of evidence too, one that is easy to overlook. Uranus spins quickly. A single day on Uranus, one full rotation of the planet, lasts only about 17 hours. That is fast, faster than a day on Earth, on a world nearly 4 times our width, and that rapid spin is difficult to reconcile with a gentle, gradual tilting process. But it fits naturally with a giant impact, which could have delivered not only the tremendous sideways blow needed to tip the planet, but also the angular momentum needed to set it spinning at the rate we see today. The tilt and the spin, in the impact picture, are 2 halves of the same ancient blow. As the researcher Jacob Kegerais, one of the scientists who has spent years building these collisions inside computers, has put it, this was almost certainly caused by a giant impact, but we know very little about how this actually happened. Hold both halves of that sentence at once, almost certainly a giant impact, and yet we know very little. That is the peculiar honesty of this field. The broad shape of the story is compelling, the details remain wrapped in shadow, and some of those details are so demanding that a growing number of researchers have begun to wonder whether a single impact is enough. Whether one blow, however enormous, can truly account for everything we see. The precise tilt, the exact spin, the specific arrangement of the moons and their orbits. And so, an alternative has emerged, one that is somehow even more startling than the first. Not one impact, but 2. A 1-2 punch, as it is sometimes called, a pair of collisions, arriving in sequence, each contributing its share to the final configuration. In this picture, Uranus was not toppled by a single catastrophe, but by a series of them, struck and struck again in its violent youth, the second blow refining and reshaping what the first had begun. Whether it was 1 impact or 2, whether the impactor was as massive as Earth or twice that, the essential story holds. A young world going about the ordinary business of forming and spinning in the early solar system was struck by something vast, and the blow changed it forever. But this raises a question that we must set down now, carefully, like a stone we will return to pick up much later. It is perhaps the deepest question in the whole affair, and it will haunt everything that follows. Where did the impactor go? Think about it. A body the size of Earth, or larger, does not simply vanish. It does not strike a planet and dissolve into nothing. All that mass, all that rock and ice and metal, had to go somewhere. And so we are left with a puzzle that is genuinely unresolved, a fork in the story that leads to very different answers. Did the impactor merge entirely into Uranus, sinking down through the wreckage to become part of the planet's deep interior, buried forever beneath thousands of miles of ice and gas? Or was it torn apart on impact, its material flung outward, scattered into a hot disk of debris that would eventually cool and condense into new worlds? Or some of both, part of it swallowed, part of it thrown clear? We do not yet know, and that not knowing is not a small gap. It sits at the centre of some of the most intriguing questions about Uranus, including, as we will find much later in this story, the tantalizing possibility that a piece of that ancient world is still down there, buried in the planet's interior, silently shaping its behaviour to this very day. But that is a thread for another hour. For now, let it be enough to feel the strangeness of the question. Somewhere in the deep past, two worlds became one, and we still cannot say exactly what happened to the second. Rest with that for a moment, and then let us follow the debris. Because if part of that shattered impactor was flung outward rather than swallowed, and the models strongly suggest that a great deal of material was indeed thrown clear, then the aftermath of the collision would have been extraordinary. Imagine the scene, 4 billion years ago, in the moments and years and centuries after the blow. Uranus, freshly toppled, wrapped now in a vast cloud of vaporized rock and ice, its own outer layers blasted loose, mingled with the pulverized body of the world that struck it. A hot, glowing disk of debris spinning around the newly tilted planet, ringing the fallen equator like a temporary halo of fire. This disk did not last as a disk. Disks of hot debris around young planets rarely do. Instead, as it cooled, as the vaporized material shed its heat into the surrounding dark and began, slowly, to condense back into solid grains, something remarkable happened. The disk began to spread and clump. The scattered material orbiting in the tilted plane started to draw together under its own gravity, colliding and merging, grain building into pebble, pebble into boulder, boulder into moon. Out of the wreckage of the collision, new worlds began to form, and this is the crucial insight, the thing that closes the loop and explains the smoking gun. Because the debris disk formed in the plane of the tilted planet, around the fallen equator, in the orientation the impact had just created. The moons that condensed from it inherited that same orientation. They did not form in the old plane, the plane Uranus had occupied before the strike. They formed in the new one, and so they orbit to this day, in the tilted equatorial plane sharing the wound, because they were built from the wound. The moons are not survivors of the catastrophe. In the leading picture, the regular moons of Uranus are the children of it, assembled from the very material that the impact tore loose. This reframes everything about how we should look at that quiet, tipped-over system. The rings, the 24 moons, the whole orderly procession wheeling around the fallen axis. This is not a family that endured a disaster. It is a family that was born from one. The impact did not merely knock Uranus over, it rebuilt the planet's entire household from scratch, out of the ruins of two worlds. And if you want the single clearest witness to that violent reassembly, the one object in the system that seems to wear the whole traumatic history on its face, you must look at the innermost of the major moons, you must look at Miranda. Miranda is small, only about 300 miles across, a modest, icy body that you might expect to be smooth and dull and unremarkable. It is anything but. When Voyager 2 turned its cameras on Miranda during that single afternoon, it revealed one of the most bewildering surfaces in the entire solar system, a face so strange that scientists have struggled to explain it ever since. It looks, in the most literal sense, like a world that was taken apart and put back together by something that was not paying close attention. A patchwork, a quilt of mismatched terrains jammed against one another with no apparent logic, as though pieces of several different moons had been shattered and reassembled into one. Across its surface run three vast, distinct features, enormous oval and chevron-shaped regions, each unlike the others, that geologists have named with a curious poetry: Arden, Inverness, and Elsinore. These are the coronae, great structures of concentric ridges and grooves and cliffs, some of the cliffs plunging for miles, forming what may be among the tallest sheer drops anywhere in the solar system. And around and between these coronae, the terrain simply does not match. Old cratered ground abuts young grooved ground. Smooth plains meet chaotic ridges. It is a surface that seems to have been broken and refrozen, sliced and stitched, without ever settling into the calm uniformity of an untroubled world. The planetary scientist Bill Botke has spoken of the absolute weirdness of Miranda, and the phrase is apt, because Miranda's strangeness sits at the heart of an ongoing debate, one that echoes the larger mystery of the whole system. Some researchers argue that Miranda's tortured surface is the product of internal forces, of tidal heating, the gravitational kneading of the moon by Uranus and its siblings, which could warm the icy interior and drive a kind of slow, cold volcanism, resurfacing the moon in patches over vast stretches of time. In this view, the patchwork is written from the inside out. But others look at that same battered, mismatched face and see something more violent. They see the signature of catastrophic fragmentation, a moon that was shattered by impacts perhaps more than once, its pieces flung apart and then drawn back together by gravity, reaccumulating into a single body that never fully healed the seams. In this reading, Miranda's coronae and mismatched terrains are not the marks of gentle internal warmth, but the scars of repeated destruction and chaotic reassembly. A moon broken and rebuilt, until it froze in its current mismatched state. We cannot yet say with certainty which story is true. Very likely, elements of both played their part. But whichever it is, the deeper meaning is the same, and it points back to that ancient blow. Miranda stands as a concrete, visible record of a system that was forced to reorganize itself from the wreckage of its own youth. Whether it was kneaded from within or shattered from without, this little moon is a monument to violence and reassembly, orbiting closest of all the major moons to the wounded giant at the center. And so the picture comes together, piece by piece, from that single afternoon of data and 4 billion years of reasoning backward. A planet lying on its side. A whole system of rings and moons tipped over with it, sharing the wound, born from the wound. A collision of almost unimaginable force, one blow or perhaps two that toppled the world without destroying it. A debris disk that cooled into new moons in the new tilted plane, and a small, tortured moon whose broken face may be the clearest surviving witness to the whole catastrophe. But we have not yet felt the full consequence of that 98 degrees. We have understood how the tilt came to be and how it reshaped the family of the worlds around the planet. What we have not yet done is stand on the surface of that fallen giant in imagination and experience what it actually means to live on a world that faces the sun one pole at a time. Because the tilt did not only rearrange the moons, it rearranged time itself on Uranus, stretching the ordinary rhythm of day and night of summer and winter into something so slow and so strange that it hardly resembles seasons at all. On this rolling world, the sun can rise and stay risen for the length of a human lifetime, and then set and stay set for just as long. To understand what that feels like, we have to leave the moons behind and travel down to the planet itself, to stand at one of those poles and wait, through a night that lasts 42 years, for a dawn that lasts just as long. Imagine standing at the North Pole of Uranus. Not that you could. There is no surface to stand on, only an endless deepening of cold gas that thickens towards something dense and dark far below. But imagine it anyway. Imagine a place fixed at the very top of that rolling world, and imagine that you could stay there, patient and unmoving, and simply watch the sky. You would see the sun, small and pale, no more than a bright point against the blackness, and you would see it hang there, not rise and set in the familiar rhythm we know on Earth, that daily arc from horizon to horizon and back. On the pole of Uranus, at the height of summer, the sun would circle the sky slowly, staying more or less at the same height, wheeling around and around without ever dipping below the edge of the world. It would not go down at night because there would be no night. It would simply stay, and it would stay for 42 years. Say that number slowly. 42 years of continuous, unbroken daylight. A child could be born at the start of that long summer, grow up, come of age, fall in love, raise children of their own, and reach middle age, all under the same unsetting sun, all without ever once seeing the sky go dark. On the pole of Uranus, a human lifetime is barely long enough to see one full turn of the seasons. Here is where the arithmetic becomes almost unbearable in its strangeness. Uranus takes 84 Earth years to travel once around the Sun, 84 years for a single Uranian year, and because the planet lies almost perfectly on its side, that 98 degrees we've followed all this way, the poles are not on the top and bottom of the world as they are on Earth. They're on the sides. As Uranus rolls along its long, slow orbit, first one pole points almost directly at the Sun, then the other. For roughly the first half of that 84-year journey, one pole is bathed in constant light, while the other is buried in constant dark. Then, gradually, the planet rolls around the far side of the Sun, and the arrangement reverses. The lit pole goes dark. The dark pole comes into the light, so each pole gets its turn. 42 years of day, then 42 years of night. Let that settle for a moment. On the winter pole, the darkness is not a night in any sense we would recognize. It is not the darkness that ends at dawn, not the darkness you sleep through and wake out of. It is a darkness that lasts longer than most people alive have been alive. A darkness in which the temperature falls and falls and there is nothing to arrest it, no sunrise coming to soften the deep freeze, no reprieve for 4 decades. And then, when the light finally returns, it does not return as a single morning. It returns as a slow brightening across years, a dawn measured not in hours but in the turning of a planet through a quarter of its enormous orbit. This is the most extreme seasonal cycle anywhere in the solar system. Nothing else comes close, and it is, when you strip it all the way down, a direct and permanent consequence of the ancient blow. The tilt that some vast body carved into this world 4 billion years ago did not merely tip the planet over. It reached into the very rhythm of time on Uranus and stretched it beyond all recognition. It took the ordinary alternation of light and dark that every planet knows and pulled it apart until a single day at the pole became longer than the reign of empires. The wound is not just written in the tilt, it is written in the clock. Now, here is the part that turns intuition inside out. On Earth, we all know where the heat is. The equator is warm, the tropics steam, and the poles are locked in ice. This makes such obvious sense to us that we rarely stop to think about it. The sun stands high over the equator, its light falling straight down, concentrated and fierce. At the poles, the same sunlight arrives at a shallow glancing angle, spread thin across the curve of the world, and much of the year the sun barely clears the horizon at all. More sunlight to the middle, less to the ends. Warm belly, cold caps. That is simply how a planet is heated. But Uranus does not obey that rule. Because it lies on its side, the geometry of its heating is turned upside down. Over the course of one full Uranian year, it is the poles, not the equator, that receive the most total solar energy. Think about that. The place that endures 42 years of darkness also endures 42 years of relentless, unbroken sun. And when you add up the energy delivered across the whole long orbit, the poles come out ahead. The equator, by contrast, never gets the sun standing high overhead the way Earth's tropics do. On this rolling world, the equator is the region that gets the raw deal. By every intuition we carry, the poles of Uranus should be the warmest places on the planet, and the equator should be the coldest. And yet it is precisely the reverse. Stop and feel the weight of that. Despite the poles drinking in more sunlight than any other part of the world across a Uranian year, it is the equator that stays warmer. The heat is where it should not be, and it is missing from where it should be. This is not a small discrepancy that scientists can wave away. It is a genuine thermal mystery, one that has puzzled planetary scientists for decades and puzzles them still. A world is being heated from an impossible geometry, and the atmosphere is somehow shuffling that heat around in a way that no one has fully explained. Something is redistributing warmth from the sunlit poles toward the equator, or holding it away from the poles, or moving it through the deep interior along paths we have not yet mapped. We know the pattern. We do not fully know the mechanism. This too traces back to the collision. The bizarre seasonal machine, the poles' warmest yet not geometry, the strange internal shuffling of heat, none of it would exist if some ancient body had not struck this world and knocked it flat. The impact did not simply mark the planet and leave. It installed a permanent running engine of strangeness, one that has been driving Uranus's atmosphere and thermal behavior for billions of years and drives it to this day. The tilt is not a healed scar. It is an open wound that the planet has been living inside ever since. And when we finally sent a spacecraft to look, the wound was hiding. When Voyager 2 swept past in January of 1986, it arrived during the southern summer. The South Pole tilted toward the sun, soaking up its 42-year day. What the spacecraft's cameras returned was a world of almost eerie serenity. A pale blue-green ball, smooth and featureless, showing none of the swirling bands and great storms that give Jupiter and Saturn their restless marbled faces. Where the other giants churned, Uranus seemed to sit perfectly still, a calm, blank, sleeping planet. That single glimpse defined Uranus for a generation. The textbook verdict was written. Here was the quiet giant, the inert one, the dull cyan orb where nothing ever happened. But that verdict, we now understand, was a seasonal illusion, a snapshot taken at exactly the wrong moment, or perhaps exactly the wrong moment to reveal the truth. Voyager caught the planet in the depths of its summer stillness and mistook a season for a personality. Because Uranus is not calm at all. It only looks that way sometimes. In the decades since that flyby, the Hubble Space Telescope and the great ground-based observatories have kept watch on this distant world, tracking it patiently across years and then decades as it rolled along its orbit, and they have seen it wake up. As Uranus approaches its equinox, the moment when the sun crosses over its equator and both poles receive light, the atmosphere stirs, storms appear, bright clouds bloom and drift across the disk. The featureless ball that Voyager photographed begins to show texture, movement, weather. The planet that seemed dead was only dormant, its activity keyed to a rhythm so slow that a single afternoon's visit could never have captured it. The engine driving this awakening is a system of powerful winds. Uranus carries strong zonal winds, winds that blow in broad bands parallel to the equator, streaming around the planet at tremendous speed. At their fiercest, they can reach some 900 kilometers per hour. Let me put that in perspective. That is well over 500 miles per hour, faster than a cruising jet airliner, faster than almost any wind that has ever blown across the face of the Earth. These are not gentle breezes drifting across a placid world. They are enormous rivers of frigid air racing around the planet, and they carry the storms with them. The storms themselves are built from methane. Deep in the atmosphere, that same methane that gives Uranus its blue-green colour, soaking up the red light of the distant sun and reflecting back the cool tones we see, can rise, cool, and freeze into clouds of methane ice crystals. When warmer gas wells up from below, it lifts moisture into the higher, colder layers, and there the ice clouds form and brighten. These are the seasonal storms that Hubble and the ground observatories have watched come and go, bright patches of methane cloud, driven by upwelling from the deep interior and carried on those racing zonal winds. And the process, we now understand, is more active than anyone believed in the quiet years after Voyager. The planet is not just responding to sunlight from above, it is also being stirred, gently but persistently from below, which brings us to one of the strangest reversals in this whole story. For nearly 40 years, the settled understanding was that Uranus had almost no heat of its own, that it was, in the truest thermal sense, running cold. But careful reanalysis of the data has begun to revise that picture. Recent work indicates that Uranus does in fact radiate more energy than it absorbs from the Sun, that it is not in the perfect thermal balance Voyager seemed to show. The figure that emerges from these analyses is that the planet emits roughly 12.5% more energy than it receives. There is warmth down there, leaking slowly outward, a faint internal glow, residual heat left over from the planet's formation, or perhaps from its violent youth, still radiating away into the dark after all these billions of years. But, and this is the crucial qualifier, even with this revision, Uranus remains an outlier. Even if it does emit that extra fraction of energy, it emits vastly less than any of its siblings. The warmth is real, but faint, a whisper of heat where the other giants pour out a roar. And so the reawakening we now observe, the storms and the winds and the upwelling clouds, becomes stranger still, an atmosphere this active, driven by an interior this cold, on a planet heated from a geometry this impossible. This is why so much of what we thought we knew about Uranus rests on such a fragile foundation. The planetary scientist Amy Simon, reflecting on the long-running debate over the planet's heat, put it with striking simplicity. Everything, she said, hinges on that one data point, the measurement Voyager took in a single pass nearly 4 decades ago, during a period we now suspect was disturbed by unusual solar weather. One spacecraft, one afternoon, one reading, taken at what may have been an anomalous moment that shaped the story of an entire world for a generation. When your whole understanding of a planet's inner life balances on a single point of data, every reassessment can send tremors through everything you thought was solid. Let me try once more to give you a feel for what all of this means, because it is easy to lose the thread among the numbers and the qualifications. Picture the planet again, a world nearly 4 times the width of Earth, rolling on its side through the outer dark, so far from the sun that our star is little more than a brilliant point in its sky. At its poles, time has been stretched into something monstrous and slow. 42 years of light, 42 of dark, a rhythm too vast for any living thing to feel as seasons. The heat that arrives falls in the wrong places, pooling toward the poles across the long year, and yet somehow leaving the equator warmer. The winds tear around the planet at hundreds of miles an hour. Storms of frozen methane bloom and fade on a schedule measured in decades. And beneath it all, the interior gives off only the faintest breath of its own heat, a dying warmth barely distinguishable from cold. Every one of those features points back to the same origin. The tilt, the stretched time, the impossible heating geometry, the cold heart, all of them are consequences, direct or tangled, of that ancient collision. The atmosphere behaves oddly precisely because it is being heated in a way no atmosphere was designed to handle, wrapped around a planet that was struck and toppled before life had even taken hold on Earth. The weather is not simply weather, it is a 4-billion-year-old response to a single catastrophic afternoon. And that faint internal warmth, that whisper of heat, so much smaller than it should be, leads us to the deepest anomaly of all. Because whether the true figure is near perfect balance or a modest 12 or 13% excess, one fact does not change. Among the giant planets of our solar system, Uranus is the cold one, uniquely, stubbornly, inexplicably cold. To understand how strange that is, we have to understand what its siblings do. Jupiter, the king of planets, radiates far more energy into space than it receives from the Sun, nearly twice as much by some measures. It has its own furnace. As the enormous planet slowly contracts under its own gravity, that contraction releases heat, and that heat pours outward. Jupiter is, in a real sense, still finishing its birth, still settling, still glowing with the leftover fire of its formation. Saturn does the same, and in fact radiates even more excess heat relative to what it absorbs, driven by processes deep in its interior. These worlds are not merely warmed by the distant sun, they're warmed from within, by their own vast bulk still slowly compressing itself down through the ages. And Neptune is the one that truly sharpens the mystery. Neptune is Uranus's near twin, almost the same size, almost the same mass, formed in the same cold outer reaches of the solar system, made of much the same stuff, an ice giant just like its neighbour. By every reasonable expectation, these two worlds should behave alike. Yet Neptune blazes with internal heat. It radiates far, far more energy than it receives from the Sun, so much that it drives some of the fastest, most violent winds in the entire solar system, on a planet even farther from the Sun's warmth than Uranus is. Neptune, sitting out in deeper cold, runs hot. Uranus, closer in, runs cold. Two nearly identical worlds, two utterly different inner lives, and no one has fully explained why. That contrast is the heart of the scandal. Because if you set the two ice giants side by side, matched in size and composition and origin, and you ask why one glows with internal heat while the other lies nearly dead, you are left with a single obvious difference between them. One of them was struck. One of them was knocked onto its side. One of them carries, in its 98-degree tilt, the mark of a collision so violent that it toppled the entire world. The measured coldness reaches all the way to the top. Uranus's cloud tops sink to around minus 224 degrees Celsius, about 49 degrees above absolute zero on the Kelvin scale, the point beyond which nothing can get any colder at all. That is the coldest temperature ever measured anywhere in the solar system. Colder than Neptune's cloud tops, though Neptune is far more distant. Colder than the farthest reaches we have directly sampled. On this world, the sky itself brushes up against the absolute limit of cold. There is scarcely any warmth left in it to lose. For decades the verdict was stark and simple. Uranus was the giant planet with no internal heat source, the dead one. The world in near-perfect thermal equilibrium, giving back to space almost exactly what the Sun handed it, and nothing more. That was the story Voyager's single measurement wrote, and it stood, largely unchallenged, for nearly 40 years. It was the great scientific scandal at the centre of this world, a giant planet that broke the fundamental rule its siblings all obeyed. Every other giant burned with its own inner fire. Uranus, alone, seemed to have gone out. The recent revisions soften that verdict without overturning it. Newer studies, drawing on advanced computer modelling and a careful re-examination of old and new data, suggest that Uranus does radiate an excess, that figure of roughly 12.5 to 15% more energy than it absorbs. So the planet is perhaps not entirely dead. There is an ember still glowing somewhere in its depths. But an ember is not a furnace. Even by the most generous of these new estimates, Uranus remains a profound outlier, giving off only a small fraction of the internal heat that Jupiter and Saturn and Neptune pour into the dark. Whether you call it near dead or merely dying, the conclusion is the same. This is the coldest heart of any giant in our solar system, and so we return, as we always must, to the through line. Why? Why should this one world, born alongside its twin in the same cold nursery, have so little warmth left in its core? The leading suspicion is the collision. Scientists have proposed that the same catastrophic impact that tilted Uranus 98 degrees onto its side may also have reached down into the planet's deep interior and disturbed its heat. The idea takes a few forms. In some versions, the blow was so violent that it dredged up the planet's primordial warmth, the leftover heat of formation, and vented it, allowing that ancient energy to escape into space far faster than it otherwise would have, so that the planet has been running on empty ever since. In others, the impact disrupted the internal structure of the world, rearranging the layers in such a way that heat could no longer flow freely from the core to the surface, perhaps trapping it, perhaps letting it bleed out, perhaps freezing the whole slow circulation that keeps the other giants warm. We cannot yet say which of these, if any, is the true account. The honest answer is that we do not know. This is one of the great open questions still hanging over the wounded world. But the shape of the mystery is clear, and it is compelling in its symmetry. The event that toppled the planet may also be the event that chilled it. The same blow that stretched its days to the length of human lives, that flung its heating geometry upside down, that shattered and rebuilt its moons, that same blow may have reached into the very heart of the world and put out its fire. Which leaves us with the question that this whole strange, cold, tilted story keeps circling back toward. Is Uranus truly dead inside, a spent world, its interior long since gone still and silent, radiating only the last faint traces of a warmth that can never renew? Or is there something else down there, something sluggish and hidden, a deep interior still slowly recovering from a wound 4 billion years old, still processing the shock of that ancient collision in ways too slow and too deep for us to have yet detected? To even begin to answer that, we have to stop looking at the surface, at the tilt and the seasons, the storms and the winds and the cloud tops brushing against absolute cold. We have to go down, past the blue-green haze of methane, into the crushing dark of the planet's interior, and ask what the impact might have done to the very structure of the world it struck. We have to ask whether that ancient blow could have reached deep enough to freeze the heart of a giant. So let us go down. Let us leave the cold cloud tops behind, the blue-green haze, the methane skin, the storms that flare and fade across a face that once looked so calm, and descend into the body of the planet itself. This is a journey no probe has ever made, and none is likely to make for a very long time. Everything we know about the inside of Uranus is inferred, deduced, reconstructed from the pull of its gravity, the shape of its magnetic field, and the behavior of matter in laboratories on Earth, where scientists have tried, in fractions of a second, to recreate the pressures found thousands of kilometers beneath its surface. But even inferred, even reconstructed, the picture is astonishing, and it may hold the answer to why this world runs so cold. Picture the descent. The atmosphere thickens as you fall. The hydrogen and helium around you grow denser, warmer, heavier. until the very idea of a boundary between gas and liquid stops making sense. There is no surface here. There is no ground to land on, no crust to stand upon. There is only a gradual, seamless thickening, gas becoming fluid, becoming something stranger still, as you sink deeper into the crushing dark. And then you reach the mantle. This is where Uranus stops being a planet you could imagine and starts being something almost impossible to picture. The mantle of Uranus is not rock. It is not molten metal. It is what planetary scientists call, with a kind of resigned imprecision, the ices, though there is nothing icy about it in any ordinary sense. It is a hot, dense, supercritical fluid, an ocean without a shore, made of water and ammonia and methane all pressed together and heated to thousands of degrees. Water that is not liquid and not steam, but something in between, something that has no name in everyday language because nothing on Earth's surface has ever behaved this way. This is the bulk of the planet. This vast, hot, electrically strange ocean is most of what Uranus actually is, and it is here, in this mantle, that the collision may have left its deepest mark. The suspicion runs like this. In the other giants, in Jupiter, in Saturn, in Neptune, heat rises. The warmth left over from formation, the primordial fire of gravitational collapse 4.5 billion years ago, works its way slowly outward from the deep interior toward the surface, carried by great churning currents of rising and falling fluid. Convection, the same process that stirs a pot of soup on a stove, moving hot material up and cool material down in an endless slow overturning. This is how a planet stays warm. This is how it releases the heat of its birth over billions of years, gently, gradually, radiating that ancient warmth into space long after the fire that made it has otherwise gone out. But what if that overturning stopped? Here is one version of the hypothesis. When the impactor struck, that protoplanet perhaps twice the mass of Earth, slamming into the young Uranus and knocking it onto its side, the blow may have done more than tip the planet over. It may have reached down and rearranged the interior itself. Instead of a smoothly mixing body where heat flows freely from core to surface, the collision may have left behind a layered world, an interior divided into stable strata that do not mix, that sit atop one another like the settled contents of a bottle left undisturbed for years. And a layered interior is a trapped interior. Heat cannot rise through a barrier it cannot cross. The warmth of the core in this picture is not gone, it is imprisoned, sealed beneath a thermal blanket of the planet's own making, unable to reach the surface, unable to escape, quietly held in place by an internal architecture that 4 billion years ago was violently rearranged. Let that settle for a moment. Not a planet that lost its heat, a planet whose heat cannot get out, a furnace still burning perhaps somewhere down in the deep, but a furnace behind a locked door, and the collision was what turned the key. There is another version, darker in its implication, simpler in its mechanism. In this account, the impact did not trap the heat but expelled it. The blow was so enormous, so violent in its energy, that it dredged up the primordial warmth of the young planet and vented it into space, allowing billions of years' worth of heat to bleed away in a geological instant, so that Uranus emerged from the catastrophe already cooling, already running low, an engine that had lost most of its fuel before it had properly begun to run. In this picture, the planet is not hiding its heat behind a blanket. It simply has less heat to give, because so much of it was thrown away in a single ancient moment. We do not know which of these is true. It is possible that neither is, that the coldness has some other cause we've not yet imagined. It is possible that both played a part. This is one of the genuine open questions still hanging over the seventh planet. And anyone who tells you they know the answer with certainty is telling you more than the evidence allows. But notice the shape of the comparison, because the comparison is what makes the case so compelling. Neptune. Remember Neptune, Uranus's near twin, the fourth of the giants, so similar in size and mass and composition that the two worlds are often spoken of in the same breath. Neptune formed in the same cold outer reaches of the solar system from the same kind of material at roughly the same time, and Neptune is warm inside. Neptune radiates far more energy than it receives from the distant sun, a strong, healthy internal heat, the ordinary warmth you would expect from a giant planet still releasing the fire of its formation. Two worlds, nearly identical, born as siblings in the same nursery. One of them still glows from within. The other has almost gone dark. Stop and feel the weight of that. If Uranus's coldness were natural, if it were simply the way ice giants are, then Neptune should be cold too. But Neptune is not cold. Neptune behaves exactly as the textbook says a giant should. It is Uranus that is the exception. It is Uranus that breaks the pattern. And when you have two nearly identical things, and one of them is normal and the other is not, the scientific instinct is to ask what happened to the strange one. What did the strange one go through that the normal one did not? We already know the answer to that question. We've known it since the very beginning of this story, written across the sky in the 98-degree tilt of the planet's axis. One of these twins was struck. One of these twins was toppled, tipped, laid on its side by a collision so vast it rearranged the whole geometry of the world. And it is that same struck, toppled, rearranged twin that has somehow lost the warmth its brother still keeps. The wound and the coldness are found on the same planet. The undamaged twin is warm. That is not proof. But it is a coincidence so precise, so pointed, that it is very hard to look away from. The collision tilted the planet, and the collision may have chilled it, and the two facts sit side by side on the same world like the entrance and the exit of a single wound. This is the through line, reaching now into the very core of the planet. The damage done in Uranus's youth is not a scar on the surface. It may go all the way down. It may be shaping the planet's energy budget 4 billion years later, deciding even now how much heat this world can release into the dark, holding an ancient fire captive behind a door that was slammed shut in the planet's infancy and has never since been opened. But the mantle of Uranus is not only a possible prison for heat, it is also a place where something extraordinary is happening, a chemistry so strange that when scientists first proposed it, it sounded less like physics than like fantasy. Down there, in that hot, dense ocean of water and ammonia and methane, it may be raining diamonds. Let me try once more to give you a feel for where we are. Several thousand kilometers below the cloud tops, the pressure climbs past 1.5 million times the atmospheric pressure at Earth's surface. Say that slowly. 1.5 million times. The weight of the entire atmosphere of our planet, the whole ocean of air that presses down on your shoulders every moment of your life without your ever feeling it. Multiply that by more than 1 million, and you begin to approach the crushing dark of the Uranian mantle, and the temperature there reaches thousands of degrees. Pressure that could flatten anything we have ever built. Heat that could vaporize any structure we know. This is the environment we're asking you to imagine. And in that environment, methane cannot survive. Methane is a simple molecule, one carbon atom bound to 4 atoms of hydrogen. It is the same gas that gives Uranus its blue-green colour, absorbing the red light of the sun high in the atmosphere. But methane is only stable within a certain range of conditions, and the deep mantle is far, far outside that range. Under those pressures, under that heat, the molecule breaks apart. The bonds that hold the carbon to its hydrogen simply cannot endure, and the carbon, freed from its molecule, finds itself under a pressure so immense that it does the only thing carbon does under such conditions. It crystallizes. It compresses into diamond. The very same substance that we prize on Earth as the hardest of gems, the most concentrated of treasures, forms spontaneously in the depths of Uranus as a simple consequence of physics. Carbon squeezed until it can be nothing else. And these diamonds, denser than the fluid around them, do what dense things do in a fluid. They sink. They fall slowly through the hot ocean of the mantle, drifting down toward the deep interior, a soft, glittering precipitation descending through the dark. A rain of diamonds falling perhaps for billions of years, falling right now as you listen, in a place no eye will ever see. Rest with that for a moment. Now, when a claim like this first appears, the reasonable response is skepticism. It sounds too poetic, too neat, too much like something invented to make a documentary sound grand. And for a long time it was exactly that. A theory, a calculation, a suggestion of what the physics implied but no one had ever confirmed. Until scientists found a way to bring the depths of Uranus into a laboratory on Earth. They could not, of course, reproduce the mantle itself, but they could reproduce, for the barest sliver of an instant, the conditions inside it, using enormous machines called X-ray free electron lasers, instruments at facilities like ESLAG in California and the European XFEL in Germany, among the most powerful light sources humanity has ever constructed. Researchers took a material rich in carbon and hydrogen and hit it with a shock wave, compressing it in a fraction of a second to the kind of pressure and temperature found deep inside an ice giant. Shock compression, they call it. A controlled, momentary recreation of the crushing dark. In some experiments they used polystyrene, an ordinary plastic, a hydrocarbon not so different in its essentials from the methane of the Uranian mantle, and squeezed it, and then looked, with the laser's brilliant light, at what had formed in that instant. And there they were, diamonds. Tiny ones, nanodiamonds, crystals almost unimaginably small, but unmistakable, formed exactly as the theory predicted. Carbon wrenched from its molecule and compressed into gem in the blink of an eye. The experiment did not prove that Uranus rains diamonds, but it proved that the chemistry is real. It proved that under the conditions found in the mantle, carbon does precisely what the diamond rain hypothesis requires. And if it happens in a laboratory in a fraction of a second, then over the vast slow reaches of geological time, in a mantle the size of several Earths, those tiny crystals may have all the time they need to grow, to gather more carbon, to build themselves into larger and larger stones, glittering and heavy, sinking through the dark toward the core. But here is the part that ties the diamonds back to the cold. When something heavy falls through a fluid, it does not simply disappear. It releases energy. A diamond sinking through the mantle trades its height for warmth, converting the pull of gravity into heat and motion, exactly as a stone dropped into water stirs the water as it falls. And if diamonds have been raining down through the mantle of Uranus for billions of years, countless crystals, endlessly descending, then all of that falling may itself be a source of energy, a slow, steady release of gravitational warmth from the precipitation of gems. Some scientists have wondered whether this diamond rain might be one of the tangled threads in the great puzzle of the planet's heat, a contributor, perhaps, to the faint ember that still glows in its depths, or a stirrer of the currents that move heat and material through the interior, and more than heat, motion. As those diamonds fall and the fluid stirs, the churning of that electrically conductive ocean may do something else entirely. something that reaches all the way out to the edge of the planet and beyond into the space around it. It may help generate a magnetic field. The lead researcher on some of this work, a scientist named Mungo Frost, described diamond rain as an intriguing puzzle, and the phrase is well chosen because the diamonds may not simply be a curiosity of chemistry, but a genuine force in the life of the planet. As they fall, they carry carbon downward from the upper mantle toward the deep interior, redistributing material through the body of the world, changing the composition of one layer at the expense of another. In a planet whose interior may already be strangely layered, stratified perhaps by the ancient collision, a slow, steady transport of carbon toward the core is not a small thing. It is a process actively shaping the architecture of the world from the inside right now, 4 billion years after the blow that started it all. The honest answer, once again, is that we cannot be certain of any of this. The diamond rain is well supported by the laboratory, well motivated by the physics, but no one has ever measured it directly, and some of what it might do, the heat it might release, the currents it might drive, remains genuinely uncertain. It is a hypothesis with strong bones and unproven flesh, but it is real enough, grounded enough, that when you imagine the interior of Uranus, you should picture it. A hot black ocean under impossible pressure, and through it, forever falling, a soft bright rain of diamonds. Because there is one more thing in this story that demands an explanation, and the churning mantle, with its falling gems and its strange conductive fluid, may be exactly where that explanation lives. It is one of the most startling things Voyager 2 found in its brief afternoon at the planet, and it is one more piece of evidence that the inside of Uranus is not built like the inside of any ordinary world. The magnetic field. Every planet with a magnetic field follows more or less a set of rules. On Earth, the magnetic field is generated deep in the core, in a churning sphere of molten iron at the very centre of the world, and it emerges roughly aligned with the axis of rotation. The magnetic poles sit near the geographic poles. A compass needle points more or less north because the field and the spin are more or less in agreement. The field is centred on the middle of the planet. It is tidy. It is symmetrical. It is exactly what you would draw if someone asked you to sketch the magnetism of a world. Uranus obeys none of this. When Voyager 2 measured the magnetic field of Uranus in January 1986, it found something that no textbook had predicted and no model had prepared anyone to see. The magnetic axis of the planet is not aligned with its rotation. It is tilted, dramatically tilted, roughly 59 degrees away from the spin axis, often cited as close to 60. And that is only the beginning of the strangeness. The field is not even centred on the planet. It is offset, shoved away from the geometric middle of the world by about a third of the planet's radius, some 8,000 kilometres off-centre, as though the magnetism belonged to some other, smaller world buried lopsidedly inside the larger one. Think about what that means for the shape of the field. Instead of a neat symmetrical pattern draped evenly over both poles, Uranus has a magnetic field that is strong on one side and weak on the other, tilted at a wild angle, tumbling through space as the planet turns. The planetary scientist Carol Patty called it a geometric nightmare, and as the planet rotates, that off-centre, off-axis field wheels and tumbles in a way that opens and closes the whole magnetosphere to the solar wind, like a child cartwheeling down a hill, the field lines flinging open and snapping shut with every rotation. No stable, orderly shield. A wobbling, tumbling, lopsided cloak of magnetism that never quite settles into the same shape twice. Let me put that in perspective. Every other magnetized planet we know is, in this respect, well behaved. Their fields are roughly aligned, roughly centered, roughly symmetrical. Uranus alone is a tumbling wreck of magnetism, tilted and shoved aside and wheeling through space in defiance of every rule its siblings follow. And the question, once again, is the same question that haunts every part of this story. Why? Why is this one world so different from all the others? The answer that scientists now favour points once again into the mantle. On Earth, the magnetic field comes from the deep core. But Uranus, it seems, does not generate its field the same way. The tilt and the offset are very difficult to explain with a tidy core dynamo. A field born at the centre of a planet ought to emerge centred on that planet. Instead, the leading idea is that the magnetism of Uranus is generated not deep in the core but higher up, in a shallower layer of the mantle itself, in that churning electrically conductive ocean of water and ammonia and methane, where the fluid carries charge and its motion can weave a magnetic field the way a dynamo weaves current. A field born not in the heart of the world, but in a restless conductive shell wrapped around it, offset and asymmetric precisely because the layer that makes it is offset and asymmetric. And that brings us all the way back to where this descent began. A magnetic field generated in a shallow, stratified churning mantle, rather than a deep central core. That is exactly what you would expect from a planet whose interior is layered, divided, arranged into strata that do not smoothly mix. It is exactly what you would expect from a planet whose insides are not the tidy, uniform, freely convecting interior of an ordinary giant, but something disrupted, something rearranged, something scrambled by a force acting in its youth. The strange magnetism and the trapped heat may be two faces of the same underlying fact, an interior that is not built the way it should be, an interior that was disturbed long ago and has never returned to order. There is a complication worth naming, and it belongs to the same honesty that runs through this whole account. Some newer studies published in recent years suggest that Voyager 2 may have caught the magnetosphere of Uranus in an unusual state, squeezed and compressed by an intense gust of solar wind that happened to be blowing at the very moment of the flyby, a condition that might prevail less than 5% of the time. The magnetosphere Voyager saw may have been an unlucky snapshot, more extreme than the planet's ordinary self. But this changes only the outer weather of the field, not its inner architecture. The tilt is still there. The offset is still there. The fundamental oddity, a field that is neither aligned nor centred, is not an artifact of one bad afternoon. It is a permanent feature of the world, and it still points, insistently, toward an interior unlike any other in the solar system. So the picture assembles itself, layer by layer, into a single coherent portrait of a damaged world. A tilt written across the sky. Seasons stretched to the length of human lives. A heart gone strangely cold while its twin still burns. A mantle raining diamonds in the crushing dark. And a magnetic field tumbling lopsided through space. Born not in a deep core but in a scrambled, stratified shell. Each of these is strange on its own. Together they tell one story. The story of a planet whose whole internal structure bears the mark of something that happened to it very long ago, and whose every physical process still answers in some quiet way to that ancient blow. Which returns us at last to the question that has been waiting patiently beneath all of this, the one we set aside long ago and have never quite been able to leave behind. If a body twice the mass of Earth struck this world 4 billion years ago, tilting it and scrambling its heat and rearranging its insides, then where did that body go? A collision that vast does not simply vanish. The impactor was real. It had mass, substance, a body of its own. And when the dust settled and the young Uranus reassembled itself around its wound, that mass had to go somewhere. Some scientists think it may still be there, down in the dark, buried inside the planet it struck. Consider what that would actually mean. Not a stone left at the edge of a field after a fight. not wreckage scattered across the road. Something far stranger, a weapon that never left the wound, that sank into the body it broke and stayed there, becoming over 4 billion years indistinguishable from the thing it destroyed. This is the boldest idea in the whole story of Uranus, and it is worth approaching slowly, because it is easy to say and hard to hold. Picture the moment again, only this time follow the impactor rather than the planet. A body twice the mass of Earth sweeping in across the young solar system, meeting Uranus not in a clean glancing brush, but in something closer to a merger. Two worlds pressing into one another at speeds that turn rock to vapour, and vapour back to liquid in the span of hours. In that kind of collision, the intruder does not bounce away. It does not survive as a recognisable thing. Its outer layers are stripped and flung into orbit, some of them settling later into the rings and moons we already met. But its dense central core, the heaviest, most stubborn part of it, plunges inward. It sinks toward the heart of the planet it has just wounded. And there, in the crushing dark thousands of miles down, it comes to rest. If that happened, then Uranus is not a single world at all. It is two worlds fused into one, a planet with a foreign heart, carrying inside it the very thing that ruined it. Let that settle for a moment. Because this single idea, if it is true, does something remarkable. It does not explain one of the mysteries we have gathered across this journey. It explains almost all of them at once. Think of what we've assembled. An interior that is stratified, divided into layers that do not smoothly mix, when an ordinary giant's inside should churn freely from top to bottom. A trapped, muffled internal heat, a heart gone strangely quiet while its near-twin Neptune still burns, a magnetic field born not in a deep central core but in a shallow scrambled shell, offset and tilted in a way no other planet can match, and a density, the sheer amount of matter packed into that vast blue-green sphere, that is oddly, quietly modest, lighter than you might expect for a world of its size. Now drop a foreign core into that world and watch what happens. A dense, chemically distinct mass settling deep inside would not blend seamlessly with the material around it. It would sit there as a separate thing, a boundary, a wall that the rest of the interior cannot easily flow across. That is precisely what stratification means. Layers that refuse to mix. The foreign core becomes the reason the planet is divided against itself, and a divided interior is an interior that cannot move its heat efficiently. Heat rises through a planet by convection, by hot material floating up and cool material sinking down in great, slow, overturning currents. But if the interior is layered, walled off into strata by a buried intruder, those currents are broken. The heat generated in the deep core cannot climb freely to the surface. It is bottled up, held down, radiating out only in the faintest trickle. The strange coldness we spent so long trying to understand, the muffled heart of the ice giant, falls naturally out of a world whose insides were partitioned by a fallen body. The magnetic field follows the same logic. A dynamo cannot be generated in a deep core if that core is not doing the work, if it is a dead, dense foreign lump rather than a churning conductive furnace. Push the field-making job outward into a shallow conductive shell, and you get exactly the lopsided off-center magnetism that Voyager 2 found, a field wrapped around a core that no longer runs it. And the modest density. A buried impactor rearranges the whole internal budget of the planet, where the mass sits, how it is distributed, how tightly it is packed. The numbers shift in ways that could nudge the density toward the gently puzzling value we actually measure. One idea, 4 mysteries. This is the seductive power of the buried intruder hypothesis, its economy, its reach. It takes a scattered handful of separate oddities and threads them onto a single explanation. The trapped heat, the stratified layers, the offset field, the quiet density, all of them, in this telling, are echoes of the same buried thing. The weapon that wounded Uranus never left. It became a permanent part of the planet it destroyed, entombed in the dark, still shaping every process on the world above it, 4 billion years after the blow. It is a haunting thought, a planet carrying its own killer inside it, forever. And I want to be honest with you, in the same way this whole account has tried to be honest, because a story this elegant deserves scrutiny rather than applause. The buried intruder hypothesis is bold, and it is beautiful, and it is not proven. It faces real and serious pushback from careful people who have every reason to want it to be true and cannot yet make it work. The trouble is that when scientists try to actually build this collision, to reconstruct the crime in fine detail, the simulations struggle to reproduce the Uranus we see. It is one thing to say a foreign core sank inside and stayed. It is another to show step by step that a real impact of a real body at a real angle would leave behind exactly this planet, with exactly this tilt, exactly this ring of moons, exactly this thermal state, all at the same time. No single reconstruction has yet managed to hit every mark at once. There is a competing reading of the evidence too. Some models suggest the impact did not so much bury heat as release it, that the collision dredged up the primordial warmth stored in the young planet's depths and let it escape early, so that Uranus radiated away its birth heat prematurely and has been running cool ever since. In that version, the impactor did not need to stay entombed to explain the cold heart. It simply had to strike hard enough to open the planet's insides to the sky for a while. And then there is the softer complication we've already met, the one that keeps returning like a note held under everything. Recent studies, published in the last couple of years, suggest that Uranus is not as cold at heart as we long believed. The old picture, drawn largely from Voyager's single afternoon, showed a planet with essentially no internal warmth of its own. The newer measurements find that it does radiate a modest excess, somewhere around 12.5 to 15% more energy than it absorbs from the distant sun. Not much, far less than Jupiter or Saturn or hot little Neptune, but not nothing either. Not the dead, silent heart we once imagined. And that gentle revision matters because it slightly loosens the knot the buried intruder idea was invented to untie. If Uranus is not quite as anomalously cold as we thought, then the mystery that most urgently demanded a foreign body sunk in its depths becomes a little less urgent. The planet may still be strange, it may still be layered, still be lopsided, still be quietly wrong on the inside. But the single most dramatic reason to believe a killer lies buried within it has softened, just a little, at the edges. As the planetary scientist Amy Simon put it, with the plainness that runs through the best of this work, everything hinges on that one data point, that one flyby, that one afternoon in January of 1986, when a single spacecraft swept past and gathered almost everything we know, and then was gone, carrying our only close look with it into the dark. We built an entire theory of a world's frozen heart on 9 hours of data from a machine that never came back. And now, as we squint at those old numbers again and gather new ones from telescopes far away, the picture shifts and shimmers and refuses to hold still. The interior of Uranus remains, in the end, a glittering mystery, a world of diamond rain and possible ancient wreckage, and no way yet to reach in and know for certain which. So how do you settle a question like this, when the evidence is 4 billion years old and buried thousands of miles beneath an impenetrable sky? You cannot dig into Uranus, you cannot drop a rope into that crushing dark and haul up the truth. What you can do, what science has learned to do with astonishing patience, is rebuild the crime over and over inside a computer and see which version of events produces the world we actually have. The tool for this has a name that sounds almost gentle for the violence it models: smoothed particle hydrodynamics. Strip away the jargon, and the idea is beautifully simple. Instead of trying to solve the impossible equations of two colliding worlds all at once, you break each world into a vast number of small parcels, clusters of matter, each one carrying its own mass, its own temperature, its own velocity, its own chemistry. Then you set them moving toward each other and let the laws of physics do the rest, calculating moment by moment how every parcel pushes and pulls and heats and flows against its neighbours. You're not painting a picture of the collision, you're staging it, particle by particle, cluster by cluster, and watching what falls out. Run enough of these with enough parcels and something remarkable happens. The simulation stops being a cartoon and starts being an experiment. You can change the angle of the blow and watch the outcome change. A head-on strike straight into the planet's heart throws off one kind of debris and one kind of tilt. A grazing hit, catching the world off-centre, throws off another. You can change the speed. You can change what the impactor is made of. More rock, more ice, a larger core, a smaller one. And for each choice, the young Uranus reassembles itself differently in the aftermath, settling into a different tilt, a different spin, a different ring of moons, a different internal arrangement. The researcher Jacob Kegereis, one of the people who has spent years staging these collisions, described what these high-resolution simulations feel like to work with. Like having a brand new telescope, he said. And that is exactly right, because in a sense they are a telescope. One pointed not out into space but back through time, at an event no eye ever saw and no instrument ever recorded, reconstructed from the wreckage it left behind. You cannot observe the impact, but you can rebuild it until the rebuilt version matches the world in front of you, and when it matches, you have learned something true about a day 4 billion years gone. The hope, the dream driving all this labour is a single simulation that gets everything right at once. Not the tilt alone. The tilt has been reproduced many times over, that 98-degree topple written across the sky. Not the moons alone, though those too have been coaxed out of the debris in models that place the family of icy worlds where we find them. The dream is one collision that produces all of it together. The tilt and the rapid 17-hour spin, and the ring of moons in their tidy plane, and the stratified interior, and the trapped or dredged up heat, and the lopsided field, every strange feature of the planet emerging from one consistent set of choices about that ancient day. And here is the honest state of the work. No one has managed it yet. This is the tension that keeps the debate alive. The models are good. They're getting better every year, running on faster machines with finer detail, resolving the collision down to smaller and smaller parcels. They can nail one feature, or two, or three. But the full portrait, the whole wounded world reconstructed from a single self-consistent blow, has stubbornly refused to snap into focus. Push the simulation to reproduce the tilt, and the internal heat balance goes wrong. Get the heat right, and the rotation drifts off the mark. It is like a photograph where you can bring any part of the image into sharpness, but never the whole frame at once. That failure is not a defeat. It is a signal. It is science telling us, in its patient way, that we are missing something, that our picture of the impact or of the planet's insides or of both is still incomplete. And there is a growing sense, spoken aloud more and more often at the meetings and in the papers, of where the missing piece might finally come from. Not from another simulation, not from another squint at those weary old Voyager numbers, from going back, from returning in person to the wounded world itself. Because in the end, every thread of this story runs into the same wall, the wall Amy Simon named. Everything hinges on that one data point, one flyby, nearly 40 years gone. One afternoon of measurements standing in for an entire planet's interior, its heat, its field, its history. We have wrung that afternoon dry. We have reanalyzed it, remodeled it, argued over whether the spacecraft caught the planet in an ordinary state or a strange one, and we have reached the limit of what a single ancient snapshot can tell us. To go further, to learn whether a killer truly lies buried in that dark, or whether the heat was simply dredged up and lost, or whether the answer is something no one has yet imagined, we have to reach the planet again. And here, at last, the story turns toward the future and toward hope. The planetary science community, when it gathered to decide what it most wanted to do in the decades ahead, made a choice that would have seemed unlikely not long ago. In the great survey that sets the field's priorities, the once-a-decade reckoning where scientists argue over which worlds most deserve a mission, the highest priority new flagship, the single most wanted voyage of the coming era, is a return to Uranus, not Mars, not the moons of Jupiter, glamorous as they are. The ice giant lying on its side at the edge of the sunlit worlds, unvisited by any spacecraft since that lonely afternoon in 1986. The mission has a plain, purposeful name, the Uranus Orbiter and Probe, and its design is exactly what this whole tangled mystery has been crying out for. Not a flyby, not another 9-hour glimpse that races past and is gone. An orbiter, a spacecraft that would arrive at Uranus and stay, circling the tilted world for years, watching its seasons shift and its storms rise and its magnetic field tumble, gathering not a single snapshot but a long, patient record. And with it, a probe. A small, tough capsule designed to plunge directly into the atmosphere of Uranus, falling through the pale methane haze and down into the deepening dark, sampling the air and the pressure and the temperature and the chemistry as it goes, radioing its findings back until the crushing depths finally silence it. Think of what that would answer. The heat balance, measured directly over years from orbit, no longer resting on one flyby's numbers. The magnetic field, mapped again and again as the planet turns and the seasons change, its true architecture finally distinguished from any unlucky gust of solar wind. The interior, probed by the way the spacecraft's orbit is tugged by the mass beneath it, reading the hidden distribution of matter thousands of miles down. And the atmosphere, tasted directly by a falling probe, its composition read from the inside for the first time in the planet's history. Somewhere in all that data, if we are patient and fortunate, may lie the answer to the question that has haunted this entire descent. Is there a foreign heart buried in Uranus? Does the killer still lie entombed in the dark it made? An orbiter measuring the planet's gravity over years could sense a dense, distinct mass down in the depths, could feel the buried intruder tugging at its path, if the intruder is truly there. For the first time, the boldest idea in the story of this world could be tested not against a computer's rebuilt collision, but against the planet itself. The mission is not built yet. It is recommended, prioritized, longed for. A voyage of the coming decades, still to be funded and designed and launched, still to make the long fall outward across the years to a world so distant that its light takes hours to reach us. If it flies, those of us who first met Uranus as a pale, featureless dot may live to see it resolved at last into a place, a real world with weather and secrets and a history we can finally read. And if it flies, the first thing it will do, in a sense, is reopen a case that has been cold for 4 billion years. Because that is what Uranus is in the end. Not merely a planet, a crime scene, the frozen, preserved aftermath of a single catastrophic day, held almost unchanged across an unimaginable stretch of time. Everything we have traced across this long journey, every strange feature that sets this world apart, points back to that one violent moment. The tilt lying 98 degrees across the sky, the seasons stretched to the length of human lives, 42 years of unbroken day surrendering to 42 years of unbroken night. The heart gone quiet, muffled or dredged empty, colder in its way than any other giant's. The diamonds forming in the crushing dark of the mantle and drifting down toward the centre. The magnetic field tumbling lopsided through space, born in a scrambled shell around a core that may not be its own. None of these is a coincidence. None of them stands alone. They are all echoes, the long, slow reverberations of a single blow struck when the solar system was young. This is the deepest strangeness of Uranus, deeper than any one of its oddities. It is a world defined not by what it slowly became, but by what was done to it in an instant. Most planets are the sum of their gentle histories, of dust gathering, of gas settling, of billions of quiet years shaping them grain by grain. Uranus is the sum of a single catastrophe, and the 4 billion years it has spent unable to recover. The damage did not fade, the wound did not heal. Instead, the whole planet organized itself around the injury, and every physical process on it today, its light, its heat, its weather, its field, its glittering internal rain, still answers, in some quiet way, to that ancient violence. To understand Uranus is to read that 4 billion-year-old crime scene, still frozen in place, still waiting. It is to look at a pale blue-green sphere rolling on its side at the edge of the sunlit worlds, and to see, beneath the calm, a story of destruction so complete that the ruined world simply kept going, kept turning, kept carrying its wound through the dark, century after century, orbit after orbit, for longer than the Earth has borne life. And so the descent that began at the top of a hazy sky ends here, at the centre of a question we cannot yet answer, in the deep dark where a fallen body may or may not still lie. We came looking for a planet and found a survivor, a world that was cataclysmically broken in its youth and has spent every moment since bearing the marks of that day, its tilt and its seasons and its frozen heart, and its raining diamonds all echoes of one instant of violence 4 billion years gone. Somewhere out there, right now, in the cold and the quiet at the far edge of the sun's light, Uranus is turning. One pole leaning into a summer 4 decades long, the other resting in a night just as deep. And somewhere far below its pale, still surface, in a darkness no light has ever touched, a question waits patiently for us to come back and ask it, whether the thing that broke this world is still down there, holding it all this time in the shape of its wound. We may go and find out. And when we do, we will be reading the oldest story a planet can tell, not the story of how a world was made, but of how one was unmade, and never quite put back together, and turned quietly in the dark for 4 billion years anyway.